Sakyaji, we should start now.
Yes, sir. Yes, sir. Convener of the FDP, Professor Praveen Agrawal, co-convener Dr. Mehar, and dear participants. I, Saket Dwivedi, on the behalf of Anand International College of Engineering and Math Tech Thinking Foundation, Fazilka, welcome you to the fourth session of the FDP Scientific Computing Essentials with MATLAB, a comprehensive one-week FDP, jointly organized by Anand International College of Engineering, Jaipur, India, and Math Tech Thinking Foundation, Fazilka, India. Our today's speaker is Dr. Mehar, and his topic is numerical methods and optimization. Dr. Mehar is assistant professor at Baba Farid College, affiliated to Punjabi University, Patiala, in the Department of Mathematics, where he teaches courses and work on supporting math students and the broader math community in various ways. His research interest is involving the fractional calculus and its applications, mathematical modeling, numerical methods, computational mathematics, special functions, hypergeometric functions, and mathematical physics. He has published more than 70 research papers in national and international journals, including SCI, SCIE, Scopus Index journals. He also has published 5 book chapters in research book published by Springer. He has delivered more than 29 invited talks, keynotes in national and international workshops and conferences. He has delivered 9 expert talks in national and international FDP workshop and seminars. He has organized 9 national workshops, 2 internships sponsored by DST, 9 webinar/seminar. He is having membership of 5 academic bodies. Under his supervision, 4 students awarded PhD. He is founder and president of Math Tech Thinking Foundation, a Ministry of Corporate Affairs, Government of India approved NGO. So welcome, Dr. Mehar, sir.
Thank you, sir, for a nice introduction. And welcome to all of you, dear participant. Hopefully, all the content which we are presenting during the past 3 sessions, you are getting. And we are trying our efforts to provide everything. If there is any kind of difficulty and you are facing any kind of challenge, please always feel free to contact us. And I hope that all of you have our WhatsApp number and contact number. The participant from different time zone, you can easily reach us by using WhatsApp number. Some of the participants are attending the session through live streaming on YouTube. So I welcome to all the participants who are attending the session through the YouTube channel. So today, first of all, I would like to share my desktop. Yes. So please let me know if my presentation is visible to all of you.
It is visible.
Please assure me. Is it visible?
Yes,
Yes,
it's visible. It's visible.
Okay. So I think both the desktop are visible. My PPT and the MATLAB both are active. Okay. So in this session, my focus will be on numerical methods and optimization techniques. So various methods are there which we are trying to cover during this session. And there are some optimization techniques also. But I am not sure the whole content which we prepared can be presented during this 2 hour, but we will try to effort to make all possible so that this content will be presented during the 2 hours. Okay, so but in the first part, we are covering the numerical methods and what are numerical method and why we need these numerical methods. This is very important to understand, and how the computing tools can help us for the simplification of the numerical methods. This is also very important. There are several computing tools as I introduced you in the beginning, but once again, I am repeating the same. For the numerical method, we can use MATLAB, and also Python is there. We can use Python for the numerical methods, and MATLAB is a commercial software, but Python is open source and free available. So the beginners, and if there is any kind of challenges for the MATLAB, then the other participant also can use Python for the computing part. All type of maximum tools which are available in MATLAB for computing, we can use also Python for the same. And the syntax between the Python and MATLAB, there is a very small difference. Once you are able to understand the syntax and the code in the MATLAB, then you can easily understand and you can use Python for the same also. But in the beginning, you will have some difficulty because this is program based, and there are several type of IDE. By using the same, we can write our code and then we can run. But MATLAB is more friendly as compared to Python and the other softwares. And also we have like Mathematica, Maple is there, Scilab is there, Octave is there. Octave and Scilab, again, both are free available, but these are not friendly software as MATLAB. So MATLAB is very simple to use. Just you need to start. So why the numerical methods? Numerical methods are the technique used to approximate solutions for mathematical problem that may not have the exact solutions. There are so many problems based on the differential equations or the partial differential equations. There are so many mathematical models which we are not able to find out their solutions by using the analytical approach, but numerical methods or the theory of approximation play very important role to find out the solutions of this type of problems. These methods involve iterative procedure and algorithm to solve equations, perform integration, and handle differential equations. They are essential in scientific computing and engineering for modeling and simulating real-world phenomena where analytical solutions are impractical or impossible. There are so many problems in real life. By using the analytical approach, we are not able to implement, just like if you want to find out the or you wanted to develop the dynamic model based on the differential equations. In that case, you have to use numerical approach. Analytical approach not possible to implement, because in that case we have to we are not able to use the live data or the dynamic equation. Okay, so numerical, by using the numerical approach, we can easily implement for the dynamic model. Then common numerical method include like Newton's method for root finding and finite difference method for the differential equations, and various techniques for numerical integration and optimizations are there. So here you can see the key aspect. Very first we have is the root equations. Techniques like the bisection method, Newton-Raphson method, and the secant method are used to find out the root of the non-linear equations, as you have studied or you came to know about all these methods. And in the linear algebra, methods for solving system of equations such as Gaussian elimination, LU decomposition, and iterative method like Jacobi and Gauss-Seidel can be used to find out the solutions of the system of linear equations. Then we have the interpolation and extrapolations. So the techniques like Lagrange's polynomial and supplying interpolation are used to estimate values between known and known data points. And the fourth point we have is the numerical integration and differentiation methods like we are familiar about the trapezoidal rule, Simpson's rule, and numerical differentiation formulas help in approximating integrals and derivatives. There are so many functions by using the analytical approach, we are not able to integrate them and differentiate them. But with the help of the numerical approach or the approximate, we can easily find out their differentiation and integration. Ordinary differential equations techniques like Euler method, Rankata method, and multi-step method can be used to solve the ordinary differential equations numerically. And there are some various type of the problems also in the ordinary differential equations, which we are not able to find out their solutions analytically. But by using the numerical approach, we can easily find their solutions, and also we can study graphically and numerically both. Similarly, we have the partial differential equations, and there are various type of the familiar method, but here we are choosing finite difference method, finite element method, and spectral method. These are highly used for the partial differential equations and the models which are best or the involving these partial differential equations. And once we write the program for this based on this method, we can easily implement and we can do different type of the experiment, and we can easily develop a dynamical model by using these approaches. So here, where are the applications of these method, and why these methods are important for the use of scientific study and the engineering problems? Used in structural analysis, fluid dynamic, and heat transfer for designing and system structure. We can use these methods for in the engineering, and in the physics, essential for simulating physical phenomena such as particle interaction, wave propagation, and quantum mechanics. And in the finance, applied in option pricing, risk management, and portfolio optimization through models like Black-Scholes equations. So since when we are developing the model for this, we can get the graphical interpretation live, because that there are frequent changes in the data, just like you can see in the finance model. Okay, so in the stock market, there is very fluctuate in the market. So that's why we required this type of the model, and we can easily get to the information dynamically. Then we have the meteorology utilized in weather prediction model to simulate atmospheric dynamic and predict future weather conditions. In medicine, we employed in medical imaging like MRI and CT scans, modeling biological system and optimizing treatment plans. In computer, the fundamental in rendering techniques, simulation, and animation to create realistic visualized effect. Then we have the environmental science used in modeling climate change, pollutant dispersion, and natural resource management to understand and mitigate environmental impact. And last one, we have the aerospace. We can use these approaches for critical in flight dynamic control system design and spacecraft trajectory optimization. So these are some few examples of the applications of this method which we can apply. But the analytical approach not applicable to study this type of problems. There are some more other applications, but just we choose here some selected examples, and we are trying to present some of the example which are related to these models. So here first we have the a very simple method, and all of you very familiar about uh, bisection method, which is used for the finding the root of the equation. And the bisection method is a simple and reliable method to find the root of the function fx. It is based on the intermediate value theorem, which states that if a continuous function changes sign over an interval, then it must have a root in the interval. Okay, so these are the 5 steps which are involved to find out the solution manually, as well as the same process will be applied to find out the solution by using the computing tool. Either you are using MATLAB or the other tool like Python or R or the Scilab. Okay, so the approach will remain same, but the syntax will different. Okay, so first step we have is choose 2 point A and B such that FA and FB have opposite sign. So this is the first step, and then after we need to compute the midpoint, which is C is equal to A plus B upon 2. Then we need to evaluate FC. Then determine the subinterval AC or CB. According to the fourth step, our program will work whether AC or CB. According to that, we have to change the sign. Okay. Then last step, we have the repeat the process with the new interval until the root is found within the desired tolerance. So following these 5 steps, we can easily write the MATLAB code, and then we can get the numerical results. So here you can see, this is my MATLAB window, and here, okay, in this folder, all the content which I prepared here for you will be uploaded for you. Okay, and you can get all this and do experiment. And I hope that there will be no challenge after understanding the code and how you can write the code. If you have some new method, you can manipulate. But the most important thing is first you must have very clear about the method which you are going to write MATLAB code. Okay, once you have the clear everything, then you can follow some steps, and according to that, you are able to write the MATLAB code, and then you can execute. So here first we are going to cover bisection method. Okay, the first is bisection method. Okay, here we choose 3 examples for the solutions of polynomial. Okay, so here we will start and we will apply the 5 step and see here. So this is the bisection method. Okay, and CSC and clear we are always use before starting the sequence of statements for the programming. Okay, so here we are choosing the function. Here is, this is the function which is x cube minus 3 by 2. So, and we are using here function handle. Very simple. If and also we discuss about how we can define the function by using function handle. At the rate, here we have only one variable, so we are using here x only, x cube minus 3 by 2. Okay, later on you can manipulate this equation, but I choose here very simple equation. So first you need to choose 2 point at which the values of this function have opposite sign. Okay, so here we are choosing a is equal to 1 and b is equal to 3 in the interval. Okay, these are the 2 critical point at which the function has opposite sign. Then the tolerance we are choosing here 1e minus x. This is very small, and how much accurate is our solution. So according to that, we are choosing here, this is the tolerance. Okay, And then maximum iterations, we are choosing here 1000. How many iterations you want to use? Okay. And then according to these our 2 point, see here, we are choosing A is equal to 1 and B is equal to 3. If the both add these 2 point, if the function has opposite sign, okay, then this must be less than 0. And if the sign will be same, okay, at this point, then if FA product FB is greater than 0, then there will be error. The function must change the sign over the interval because we need opposite sign. Okay, if this condition is satisfied, then the other statement after that will not work. We have to change the values of A and B since we need the opposite sign of the functions at A and B. Okay, so only then our method will work. So that's why we apply at this place the condition whether this condition is satisfied or not. Then after we need to initialize. Okay, so this is the first iteration. This is the first iteration, and C is equal to A plus B by 2. At this place, we will take the mean of these 2 point, and we have the new value. Okay, so here we will store the iteration values. We are storing at this place the iteration values. So the value which will be computed at this place will be stored at this place automatically. Okay, C value is equal to square bracket and iteration automatically. Okay. So 0 iteration is there and the first value is there. Then after, this is the main part of our method. See, this part is very important. Only this part. Okay. So first we have while B minus A upon 2 is greater than and equal to tolerance. Okay. We consider here the tolerance is less than and equal to. And iteration less than maximum iteration. So according to that, if this condition is satisfied, then iteration is equal to iteration plus 1. This is the while loop. Okay, the new value will be at its place and the next step will be stored at its place. And then new value will be computed. C is equal to A plus B by 2. Okay, and these values will be stored at this place, C values, comma C. Okay, this is the new value. New value will be stored at this place because when we have the interval AB, see, just 1 minute, I have to choose the epic pen. Just 1 minute, please. Yes. Okay, so here is 1 and at this place is 3. And when you have the new value C, okay, C is at this place. So either you will choose this interval AC or CB. So if these two have the opposite sign, then this interval will be selected. And if these 2 points have the opposite sign, then this interval will be selected. So according to these, the value will be selected and will be stored at this place. Okay, and this is the iteration. If FC is equal to 0, okay, so at one level, the C point when becomes 0, at which the function has become 0, then this will break. This will break because at that level we have the desired value. Since the function is like in this way and the sign are opposite, and by repeating the iteration at the end we have the point C. This is the solution of the polynomial. And when we get this value at which f of C becomes 0, and this point is the solution for this interval. Okay, so when this condition is satisfied, okay, meaning that when you are applying the iterations and at one level you get this value, you are getting the point C where this become equal to 0, then this will stop and you have the solution C. Okay. If this condition is not satisfied, If this condition is not satisfied, then what? FA product FC is less than 0. The sign must be opposite. Okay. So either in that case, either B will be equal to C or A equal to C. Okay. And then we need to close if will be end at its place, and this is the end for the function. Okay. So this is the complete program for the bisection, and quite easy to write the code. Okay. And each step, how we implement and what are the meaning of the tolerance must be clear. Now we can display the result. So these statements are used to display the result. So here f print, the root is approximately x is equal to, so this will display the value and will take automatically corresponding to C, and these will represent the iterations, number of iterations, how many iterations are used. Okay, corresponding to this, and then we can display here the number of the iterations and the values at which at C corresponding to each iteration. So here you can use the display iteration C, and for I is equal to length of the iterations which has been used, and then f print is again used the function to print the value iteration. This will take the, what is I? I is the index corresponding to iterations, and again corresponding to the C values, I is used for the index. So these will return the numerical values. Okay, now we can execute these all the sequence of statement, and when you will execute, yes, you can see the root is approximately this value. X is equal to 1.144712, and the number of iterations are used here is 20. Okay, so here also the values of C corresponding to the iterations you can compare. When we have in the first iteration C is equal to 2, when we have the iteration 2, C is equal to 1.5, and you can easily compare because the interval we have is, which we choose here is 1, 3. Okay, so the first value will be value of C will be 2, 1 plus 3 by 2. Okay, and so on. So you can check all the values corresponding to the iterations, the values of C. So at the 20th iteration, we have C is equal to 1.144712, and which is the solution for this polynomial x is equal to this one. Again, if you want to manipulate, I am taking here x square, and here is I am taking 4, and then you can see I have only one iteration. I have is only one iteration. So according to the requirement desired value, okay, and that desired value depends upon this one, tolerance. Okay, so by using the tolerance, the number of the iterations will take only when the tolerance condition is satisfied, all those iterations will work. Okay, and when the condition is justified, the loop will automatically out. So you can choose here different type of the polynomials, and you can find their solutions. If you are taking here 3 by 3 upon 5, and then x raised to power, function must change the sign. So for this function, the sign are not changing this interval. So the condition is not satisfied. That's why we have this error message. The first condition is that the condition must be satisfied. Okay. If we choose here is 2, then if here is 3, now okay. If you are taking 5, since the condition must be satisfied for these 2 points, and you can change these values also. If I take here 2, you know the solution of this polynomial when we choose here 3. Okay, you can see here again the values, the function don't have the opposite sign. Okay, sign must be changed. That's why we have the error message. And if we have at this place is 0, then we have the solution. Then we have the solution. So when you have the interval 0 and 3, the sign of the function are opposite, and we have the corresponding solution. And here number of the iterations which are used 21, and x is equal to we have is 1.732050. So once you have write the program, you can find out the solutions for different polynomials. Okay, you can do lot of operations, experiments by using this program. One time you need to write. Okay. So here, this is all about the bisection method, and I hope it is clear. If you have any question, please let me know. Any question, please? Okay. So here we have the next method is Newton-Raphson, which is very useful, and various type of applications are there we can find in a different type of the problems for scientific and in engineering problems. Highly useful this method. The Newton-Raphson method is an iterative technique that uses the derivative of the function to find its root. It is faster than the bisection method, but requires the function to be differentiable. So the main thing is we need to choose the initial guess, which is x naught. We choose according our desire. Okay, compute the next approximation by using the formula. So this formula will be used xn plus 1 is equal to xn minus fxn upon f dash xn. So on the right hand side, this term involve first order derivative. Okay, and repeat until this difference xn plus 1 minus xn is smaller than the desired tolerance. So according to the our desired tolerance, this value must be less than. Okay, so when we will use the loop for the number of iterations, when this condition is satisfied, then we get the required solution. Okay, see in the MATLAB. So here I write the code for the same. Okay, so here is the code. So here CLC and clear are same. Function we are choosing here is f is equal to at the rate x square minus 4, and its derivative df is its derivative. We know its derivative will be 2x. Okay, 2 product x, or either you can use the definition of the derivative by using the diff, that also you can use at this place. Okay, so initial guess we are choosing here is 3. The value of x naught is equal to 3, which is the initial guess. Okay, and after that we are taking the tolerance value is 1a minus 6. This is very small value. This is very small value. Okay, and the maximum number of iteration we are choosing here is 1000. So we are a number of the iterations we are always choose large number, so that sometime the program when we write for the different problem, sometimes it will take large number of the iterations. That's why we must have this value. And sometimes we are not get the solution for this number of iteration which we choose. If in such case appear, then this will return the value and no solution. In this case, when this number of iterations cross this value and the desired value not get in that case. So here, how we can initialize? So here you can see the initialize the variables. First, we have the x is equal to x naught, and x naught we are choosing 3. Okay, this is the and the iteration. This is the 0th iteration. Okay, so when we are applying the for loop or while loop, in that case, we will start from the 0th iteration. So initial what we are given. So we are given here is this value. Okay. So now we are going to apply here Newton-Raphson method. So here, while absolute fx is greater than tolerance, at the end, the iteration and the iteration is less than maximum number of iteration. Okay, the number of iterations which will be used, that must be less than the maximum iterations which we choose at this place. Okay, the number of iterations must be less than 1000. Only then this code will work. So here, this is used for the, this is the loop used for number of the iterations. Okay, so first this will be taken from this place for this value. Okay, now the new value will be computed when we have x is equal to x naught. When we have x is equal to x naught, in that case, we want to calculate or we want to compute the value x1, which is the new value. So this is the new value, which is equal to x minus fx upon dfx. Okay, so this is the derivative of fx. This is derivative of fx and following the same formula which we discuss here. Xn plus 1 is equal to xn minus fxn upon f dash xn. But this code will become on the left hand side, we have the new value. When you write the code, this become new value. Okay, and here is x, then fx upon derivative of f. Okay, so this value will pass through this function. We will print here all these values numerically, and here we are using the if condition. Why? If x new minus x is less than tolerance. See this condition carefully. This one, repeat until xn plus 1 minus x is smaller than the desired tolerance. So when we have this value is less than tolerance, then break the condition. Then the loop will break and we have this will stop. Okay, so this is the condition, and when this condition is satisfied, we have the desired value, and x equal to x new, the new value will be stored at this place. Okay, so each time the value we are getting at this place will be updated here, and this value again will pass at this place for the next iteration. Okay, so here the iterations will be updated. I will start from 1, 2, 3, 4, 5. Okay, so first it will choose the value 0. So 0 plus 1 will be equal to 1. So this is the first iteration, and then first iteration will be completed. The iteration will be updated here. 1 plus 1 becomes 2. Okay, and corresponding to this iteration, the new value will be updated. So this syntax is very important to understand. Okay, then after we can display the values also. So here we have the result will be displayed here. So the root is approximately x is equal to this. This code you need to remember. So corresponding to the x value, we have the value will be printed by using this statement. Okay. And here the iteration, corresponding to the iteration, the number of iteration will be printed. Okay. So when I will execute this code, see, these are the results. You can see that the number of the iterations used for only 4 iterations. Okay. And this method is faster than the bisection. In the bisection, we have 20, 21 long iterations are required. But here we have only 4 iterations, and the root is approximately x is equal to 2. And you can see here the iteration 1, x is equal to this value. For the second iteration, this value. For the third iteration, we have this value. And for the fourth iteration, we have this value. Okay. And you can again manipulate these equations. You can choose here 3. And you can again run the code. Okay. So, yes. The root is approximately x is equal to 9, not a number, but the iterations are 13. So here, okay, because the problem is that we have to update this value also. The derivative of x cube we have is 3 x square. 3 x square. If you are taking the polynomial here, its derivative must be updated at this place. Okay. So its derivative we have is 3x square. Now, yes, it is correct now. So here 5 iterations are used to find out the approximate solution for this polynomial. Okay. You can manipulate in different way by changing the values. Now 6 iterations are there, and you can change this value also. If you are taking x is equal to 1, then what happened? Okay. 3 iterations are there. So once you write the program, you can easily manipulate, you can play the code. Okay, you can do numerous experiments by changing the values, by manipulating the equations, and so on. So just you need to understand only this part. When you apply the method, okay, and how we can write the code to implement MATLAB. And I think there is no doubt in this method, because the methods which we choose here are very simple, and code are also very simple. Just you need to understand the sequence of the statement, how we are implementing all these. Next, we have the secant method. Okay. The secant method is similar to the Newton-Raphson method, but it does not require the derivative of the function. It uses a sequence of secant line to approximate the root. Okay. So we need to choose here the initial approximate x0 and x1, compute the next approximate by using the formula. This is the formula, and this formula will be used to find out the next value. Xn plus 1 is equal to xn minus fxn into xn minus 1 upon fxn minus fxn minus 1. Okay, and also repeat until xn plus 1 minus xn is smaller than the desired tolerance. Okay, so this is required. So here is the code for the same, and we are taking the example. Few statement will remain the same. Okay, only method will change. So here we have the function, which is x cube minus 3 by 2, and the initial values we are taking the same as we choose for the bisection method, 1 and 3. Okay, and the tolerance and maximum number of the iterations, these are the tolerance value, and maximum number of iterations we are choosing here 1000. You can change this value. Okay, then here we are initializing the same. Here we are initializing. So the iteration is 0. Then we have the x values. These are the x values. And we have two values. One is x naught and other is x1. Okay. So here is the condition. This is the required condition. While see this condition very carefully. Absolute x1 minus x naught is greater than tolerance. This is the first condition. When this condition is greater than tolerance and the iteration is less than maximum iteration. If this condition is satisfied, then the other statement will work. Okay. So here first we are using for the iteration loop. Okay. So all the index will be updated at this place. And fx0 is the value at the point x naught. So the functions, the values which are involving in the function, the values which are involving in the function on the right hand side at this place, you can see when we have n is equal to 1, when we have n is equal to 1, so it will be x1 fx1 x1 minus x0 and fx1 minus fx0. So these two values we need to find out, and only then we can pass through this function. Okay. So the desired values which we need, we have to find out. So so that by the repeating the iterations, all these values can be updated. So this is the values which we are given corresponding to this point will be computed. So now the new value will be updated at this place, and this is the same formula. This is the formula x new, and x new is equal to, you can see the left hand side xn plus 1 is x new, and the right hand side you can compare with the MATLAB code. Okay, so this is x1 minus fx1 product x1 minus x0 corresponding to xn minus xn minus 1 upon divide. This is fx1 minus fx0. Okay, so the values, x values will be equal to, we need to update here x values and x new value. Okay, so these will be updated, and x naught will be equal to x1, and x1 will be equal to x new. So the new value will be stored corresponding to x1, and x naught will be equal to x1. Okay, so this value will be automatically updated for the next iteration. And after that, we need to print the value, and these statements are the same for bisection, for Newton-Raphson, no difference. Okay, we are printing the value, we are printing the number of the iteration, how many iterations are used, and corresponding to the iterations, we have the values of the action. Okay, so when you will execute this sequence of statement, you can have the solution. Okay, so the root is approximately x is equal to 1.144714. Okay, and the number of iterations we have is 7, and these are the iterations you can see, and you can observe, you can study the values of x which are changing on the right hand side. Okay, in the column for the first iteration, second iteration, and in the 7th and 8th iteration, the values are repeated. Okay, so also you can compare these polynomials which is the best solution. So if you are taking this polynomial for the bisection method also, for the bisection method, this is the bisection method. Okay, and put here, yes, if you will use bisection method for the same polynomial, but the x naught is equal to 1 and 3. We need to update these also. A is equal to 1 and B is equal to 3. Enter on the code. It will take about 20 iterations. Okay. And second method will take only 8 iterations for the same. It means second method is faster than the bisection. And if you will use the same for at this place for the bisection, okay, we are updating at this place. Yes. So the derivative of x cube will be 3x square. And check at this place, this will take only 3 iterations. So this is the fastest method is compared to the bisection and the second method. Okay, so this is the sequence. So second method is faster than bisection and Newton is faster than second method. So in this way, you can compare these methods. So this is all about the numerical method for the polynomial. If there is any question, please feel free to ask. Is it clear? Okay.
Yes, sir.
Okay, thank you. So
Yes,
once
sir.
again, I am sharing my screen. Okay. So here we have the ODE with the Euler method. We can solve the ordinary differential equations or the system of the differential equations by using this approach. Okay. So the Euler method is a numerically technique used to approximate the solution to ordinary differential equations when an analytical solution is difficult or impossible to find. It works by stepping through the ODE in small increment using the derivative at each step to predict the next value of the function. Okay, and here this is the steps which are involved in the Euler method. Okay, and we can use for first order differential equation. Okay, so here the steps which are involved, we need to discuss one by one, and then we will follow the same step to implement in the MATLAB. And very quite easy. Once you need to follow the step and following the same, we are able to write the MATLAB code. So in the very first step, we have the differential equation in the form of y dash is equal to fxy, where fxy represents the derivative of y with respect to x. Then after set the initial condition, we are given the initial condition along with this differential equation, and at the starting point x is equal to x0, we need to set to implement this Euler method. Okay, then choose the step size. Okay, we need to choose the step size, select the increment h that determine the size of the each step taken along x-axis. Okay, then after we need to iterate using the Euler method, which is defined at this place. Yn plus 1 is equal to yn plus h product f xn yn. Okay, so when we have n equal to 0, this will become y1 is equal to y0 plus h f x0 and y0. So when we have given the initial condition, okay, this right hand side we can compute and we get the y1. Okay, for x is equal to, when we have y1, then this will be value corresponding to x1, and x1 will be equal to x0 plus h. Okay, so both we need to update. We need to update this value as well as this one. So corresponding to x1, we have y1. Now these values become initial value for y2 when we have n is equal to 1. When you are choosing n equal to 1, we have y2. Okay, for y2, these become initial value, and so on. This iteration will work up to the given interval or the desired value. Okay, so we will repeat the same. So this is the last step. Continue this process for the desired number of the step until reaching the end point. This is the end point. Say if we are given, this is the interval x0 to xf. Okay, so this is the final value and this is the initial value. So we need to get this value. What we do, we will divide this interval in the sub point. Okay, and corresponding to the point which we have corresponding to the step size. Okay, we will divide this interval in the sub interval, and the length of the sub interval we have the value of h. Okay, so as much we have the sub intervals or the step size must be as small as possible, we have more accurate solution. So we will compare by changing the step size also. So this is all about the Euler method to write the MATLAB code, and this will help you to understand how we can implement in the MATLAB. See now in the MATLAB, this is my MATLAB window, and this is the folder, and in this file folder we have example 1. Okay. Select these two files, and all these .m files will be shared with you. Okay. Yes. See this Euler method very carefully and understand every step. So here we are choosing the differential equation dy upon dx is equal to x square plus y. X square plus y. And this is the initial condition, y0 is equal to 1 and xn, okay, is equal to, it means the interval we have is 0 to 2. So here you can see, first we will apply the given values of the given parametric values. So x0 is equal to 0. This is the initial value of x. And y0 is equal to 1. This is the initial value of y. Okay. And xn is equal to 2. No difference. You can write here xn or xf. Okay. Doesn't matter. So this is the last value. Okay. So xn is equal to 2. So here the interval we have is from 0 to 2. And the number of steps we are choosing here 100. So this interval 0 to 2 is divided into 100 steps. And here also we need to compute the step size. 100 steps are there, but we need also the step size. So you can compute the step size by using xn, final value, minus initial value upon n. So this will compute the step size. Okay. So then after you have x zeros 1 to n plus 1. So first we are going to initialize the arrays. Okay. and these are the zero arrays only, and later on corresponding to the values will be updated. Okay, the size of x and y both will be must be equal. Only then this code will work, or we have the desired value. If the length of these vectors are not equal, then this will not work. You don't have the numerical solution. Okay, if you want to check what are the meaning of this one, you can check it. And how you can check it? You will take these values. You need to take these values. Okay, and put these values, copy and paste here, and enter. Then check what is the meaning of this one. Copy and paste here. What is x? This is x. Okay, you can see the size of x is 1 by 101. And when you will check the values of x, double click on it, and you can see that all the values are 0. Okay, all the values are 0. So the step, we have 100 steps, the points will be 101. Okay, we have 100 sub intervals, and for that the number of point will be 101. That's why the size of x we have is 1 by 101. And you can check for the y also. You can check for the y also. Okay, copy and paste in the command window. And come to, yes, you can see this is also the same length, same size. Okay, so these are only the vectors having the same length, and later on these values will be updated corresponding to our function and the desired values. Yes. So now come here. Now we want to initialize. Okay, we will start from the initial value. X1 is equal to X0. What is the meaning of X1? This is the index. Okay, the initial values. These are the initial values. X0 and Y0 are the initial values. But when we are going to apply the loop, we need here index for the each value which are exist in the this vector. Okay, so here we have the length of the interval is 101. Okay, and we will start from the initial point, and first point is x0. Okay, so that the index is x1, and for the corresponding to y0 we have is y1. So these are the initial values we need to store at a space. We will start from the given values. Now we can apply the Euler method. Okay, as I told you that we need to update both the values. Okay, so come back. Here is I explained already. This is yn plus 1 is equal to yn plus h f xn yn. Okay, so xn plus 1 will be equal to xn plus h. Xn plus h. Okay, so for these two equations, we need to apply for loop. Okay, so first this equation used to first, then after we will write the code for this one, because this will updated, then we get the value for y, because x is independent and y is dependent. That's why this equation must be first. Now come here. Yes. So here is the same approach. At the place of n, see, very simple to implement. At the place of n, we are using I. We have xn plus 1 is equal to xn plus h, right? So this will be xi. Okay. And this can be written as xi plus 1. So this is the code. Okay. And similarly, you can easily write yi plus 1 is equal to yi plus h plus h. And what about this one? Yn plus 1 is equal to, we have is yn plus h, and here fxn yn. What is f? F is dy upon dx. Okay, so this will be yi plus 1, yn will be yi, h is h, and f is my ODE. This is the differential equation which we have to write the code separately. Okay, and xn yn, this is xi and yi. This is f. So where is f? Come back. Now I have to delete, and this is the differential equation. Dy upon dx is equal to x square plus y. We create a user-defined function for the differential equation. Okay, fxy representing the ODE dy upon dx. Okay, so we create a function with the name of my ODE differential equation, and x and y are the input argument. Dy upon dy dx is the output argument. So dy upon dx is equal to x square plus y. So this is the user-defined function, and we will call, after defining this function, we can easily call at the space my define, and these are the input arguments. Okay, so automatically what will be there? All the arrays which we defined earlier, all the values will pass through at space, and corresponding to this, by using the ILR method, all the values will be stored on the left hand side, and we are able to plot the graph now. We are now able to plot the graph. So the value of x will be stored at its place, and that of y will be stored at its place. And now for the plot numerical, we are using the very simple function plot x comma y, and this is the marker. This is the marker. Okay, hyphen and o, small o. There we have the x label, y label, and title. We have the numerical solution using Euler's method and grid on. So when you implement this sequence of statement, okay, and you can run the code, you have a very beautiful graph. Yes. So this is the solution of this differential equation, and you can, by using the Euler method, which is very simple to implement. Okay, now you can do various type of the experiment by using the same code. Just what you will do, you need to choose the different type of the differential equations. Here we have dy upon dx is equal to x square plus. If you have, here is product x. If you here is product x. Okay, this is now we have new differential equation. This is now we have Gurpreet, please mute your mic.
इमोशनल है ज्यादा, है ना?
Gurpreet Kaur, please mute your mic.
अंदर नहीं आ रहे हो, सब नहीं अंदर आ रहे हैं।
No problem.
अगर कुछ चाहिए नहीं ना हो, difficult।
Okay. So dear participant, you unmute your mic only if it is required. Otherwise, please keep muted so that there is no interruption. Okay. Once again, I am sharing my screen. Yes. So here, here you can see this is the new differential equation. I change the differential equation. Here I have is x square plus y product x. Okay. And once again, when you will execute this sequence of statement at this place, okay, and you have new solution. You have the solution corresponding to new differential equation. And close it. If here is you are taking sin x, this is sin x, and this is cube, and here minus. First you need to save this differential equation. Now this is the new differential equation. Okay, and you can execute. You have this solution. The graph is changed. So once you have write the code, you by using the Euler method, you can do several experiments. Okay, is there any doubt for this model? So whether you have the linear or non-linear differential equation for both type, you can solve by using this Euler method. Okay, whether the any kind of equation and complex problem also you can solve by using this method. If you have product exponential x. Okay, now by using the ordinary method, we are not able to find this type of the equation, but with the help of MATLAB, by using the Euler method, we can find the solution. So when you make any change at this place in this user-defined differential equation, you need to save first. First save it, then you can run this code. Okay, also you can change here the numerical values. We have this graph. Now you can see. Okay, one more thing. If I am taking here the number of iteration is only 10, then what happened? You can see the graph is in this way. And if you make it more small, only 5, then yes, you can see. So for the smoothness in the curve or the more accurate solution, we have small step size. As much you have the small step size, you have more accurate solution. Okay, got it? So here is, if you will take 100, then you have more accurate solution. And this is the graph. And again, one more thing, I want to update this value. We have the equation x square plus y. Okay. This is x square plus y. And save it. So when I share this code with you, no confusion, because we are doing for this equation. So for each method, you will have 2 files. Okay, sometimes all the code, entire code can have the single file, but every file I have created the separate folder so that there must not be any kind of confusion. So when I will share this code with you, this is the second example. This is the second example. And when I will enter, okay. So what you observe here, you can see that we create Euler method function. This is a different approach. This is another approach to write the code. Euler method, f is the function, means dy upon dx, x naught, y naught, h, and x maximum, the max value of the interval. Okay, so see here, x is equal to x naught, h is the step size, and x maximum, the last value or the end value of the interval, or final value of the interval. X maximum means final value of the interval. So the interval will start from this place and end at this place, and h will be the step size. Like I will give you one example. If you are taking the x is equal to 0 and 5, okay, then this will be in this way, and the step size is 1. If you want to manipulate, or you want to manipulate the step size according to your desired value, you can take this step size in this way: x is equal to 0, then colon point 0.01, and colon I have is 1. See very carefully. Here the step size is very small, 0.01. This is the value of h, which I highlight at the place. And when I will execute this code, you can see we have the array, x array, and the step size is very small. You can see 0, then 0.01, 0.0200, and so on. Okay, so here this is the initial value, this is the final value, and h is the step size, and we are creating the y zeros is the length of x vector as well as y must be equal, as I told you earlier. And this is the initial value which will be given to us, y1 is equal to y0. Okay, and then after our for loop will start from I equal to 2 to the length of the x, because the first index is here. I is equal to 1 used at this place, so the for loop will start from 2 to the length of x. The number of point in x and in the y must be equal. Okay, only then when you will plot the graph and you want to the numerical result, the length of each vector must be equal. Only then it is possible. And here we have the same Euler method. Yi is equal to yi minus 1 plus h f xi minus 1 yi minus 1. Okay, and you will save this function. Now you can call this Euler method function for the numerical result. See here, this is the another approach. Okay, so either you can use the first approach or you can use this approach. But here we have the same example. So here CLC, this is the function f is equal to xy, x square plus y. Okay, and x0 is equal to 0, y0 is equal to 1. The step size we are choosing here is 0.02, and maximum value we are taking at a space is 1. Now what we do, we will call the function which we create at this place. This is the Euler method. Okay, separately we create a user-defined function for Euler method, and we will call at this place. Okay, and the same argument you will take, you will copy it and paste here. Copy and paste. Everything must be same. Everything must be same. And this method, what we'll do, this will solve the values for y. Okay, so we want to store these values, and we are using this assignment. So first is x, then y. So the values of x and y both will be stored in this bracket. Okay, and then after you have the same code. This is the same code. Okay, and this is not required. We can comment this one by Control R, and when you will run this code, yes, we have the graph. We have the graph. Okay. Okay, this was uncommented. So uncomment this statement and now run the code. So this is the graph. And also along with the graph, you need some numerical values in the tabular form. And you can see in the first column, first is X vector and second is Y vector. Okay, so X, the values of X and Y are there. And how we can get these values? See, to get the numerical values, we have to use this statement. So X1 will be equal to X transpose, because transpose is used for to convert the row vector into the column vector. And Y1 is equal to Y transpose. We convert here row vector into the column vector. And Z is equal to, we have is, we want to print these values both. So that's why we are using this expression X1 space Y1. Okay, and display Z. So when you will execute, you will have the numerical values at this place. So in this way, parallelly, you can get the graphical and numerical values, both by using this type of the sequence of statement. And I hope that this discussion is very useful for you. Are you enjoying? Any question, please? Any doubt if you have? Any question from your side regarding this presentation? Harjot Singh, Dr. Aravind.
No, sir.
Hello? Okay. Sukhveer. Hello.
It's fine, sir.
Thank you.
Hello.
Jaspreet Kaur. No doubt. Thank you.
हाँ जी सर, हाँ जी, प्रेजेंट है हरजोत भी।
Okay, okay. Thank you, sir. Now, once again, I am sharing the screen.
Hello.
Okay. So here, I have the example number 2 and what inside example number 3. I have to check if there is anything new. Yes, this is the same method. You can check later on. Okay. Idle method is there inside this folder also. And small change is there. You can understand yourself. No big change. You can do. You can do yourself this part. Okay, so I have to close this folder. Okay. Now, we have finite difference method for partial differential equation. This is also again very important method. There are various type of the method for ODE and PDE. Okay, so many numerical methods are there, but within 5 days we are not able to present entire methods, but we can give some examples so that you can be familiar how MATLAB is working, how you can write the code. Okay, and if you have some understanding about this numerical approach, numerical methods, you can use for your future use. You can extend for the other methods also. So here we are going to discuss about the finite difference method for PDE, partial differential equation. Okay, so there are various type of the methods for partial differential equations, but here the method which we choose here is FDM, which is very familiar method for different type of the models which are based on partial differential equations. Okay, so the approach is discretization of the domain. So divide the continuous domain into the finite grid of the point. Then we need to approximate of the derivative, replace continuous derivative in the partial differential equation with finite difference approximation using Taylor series we can do. And then after formation of difference equation. Okay. So for that, we substituted the finite difference approximation into the PDE to form a system of algebraic equations. Then we need to imposition of boundary and initial conditions. Okay. Apply the given boundary and initial conditions to the system of the equations. And at the end, we can solve the resulting system of the algebraic equation using appropriate numerical method to obtain the approximate solution of the PDE at the grid points. So here, okay. Now for this method, I have to close this one first. And I have to open. Okay. I have to. So these are the content which we are presenting. These are the today's content, which will be later on shared with you. I have to open with the. So the, sorry. Just 1 minute, please. Yes, this one. Okay. Yes. So here we present an example how we can implement finite difference method for one-dimensional heat equation. So once you are able to understand the implementation of this finite difference method, you can use for different type of the problems which are associated with the partial differential equations. Okay. So here we choose the one-dimensional heat equation, and which is defined in this equation. Del u upon del t is equal to alpha del 2u upon del x square. Uxt is the temperature at the position x and time t, and alpha is thermal diffusivity constant. Okay. So we want to solve this equation by using this method. So first we need to discretize. Okay. And divide the spatial domain into the discrete point with the step size delta x. Okay. And del 2u upon del x square will be equal to ui plus 1 minus 2ui plus ui minus 1 upon del x square. And the time domain into the discrete step size will be equal to step size is delta t, and del u upon del t will be approximate to ui n plus 1 minus ui n upon del t. So these are the methods or the formulas to discretize, okay, which you have to remember. But we can drive, but at this place I am not in the process to drive these expressions. Just we need to follow, and we will use these expressions for this finite difference scheme. Okay. So when you will put this expression in the given heat equation, will be reduced in this form. This is the left hand side del t upon del u upon del t. This will become ui n plus 1 minus ui raised to power n upon del t. is equal to alpha. And on the right hand side, ui plus 1n minus 2 uin plus ui minus 1 n del x square. Okay. So we will solve the above expression for this one. We will solve for ui n plus 1, simplify the previous expression, and we will have final expression is in this form. And based on this expression, we will write our MATLAB code, and this iteration expression will help us to write the MATLAB code. And once we are able to write and assign the parametric values with the initial condition and the boundary conditions, then we have the numerical solution of the problem. Okay, so here and apply the boundary conditions, then we will simplify for the initial condition ux0 which we are given. We will start from this condition. Okay, and these are some manual values which we got, which we will simplify for this initial condition, which is we are given u0 is equal to sine pi x. Okay, sine pi x, this is the initial condition. And u0 will be denoted as in this form, and colon 1. Okay, so when we have time is 0, index will be 1. Okay, so these values are computed corresponding to this initial condition, and you can observe, but we can skip because we will do everything by using MATLAB. Now jump to MATLAB. Yes, so here the method has been written. Okay, this is the method. And one more thing, so you can see these are the grids. On the horizontal line, you can have the x, and on the vertical line, we have the t. Okay, so this grid will be used. What you are given? You are given the initial values. Initial value will be on the x-axis. Okay, u11, u21, u31, u41, u51, and so on. Okay, so 1 is when time is 0. When time is 0, index is 1. Okay, keep in mind. And in the same way, on the vertical line, these are the left boundary condition. Okay, and on the right hand side, we have the right boundary conditions. So the boundary conditions we are given. What we need to compute only the internal points. Okay, u2 to u3 to u4 to u5 to, okay, and all these interior points we need to compute on the basis of this initial condition and the left boundary and right boundary conditions. Okay, and we will start from the initial condition. So in the given domain, we can get all the point. See here. So all these points we can easily compute by using our MATLAB code. Yes. So here we have the example. See very carefully, and I will try slowly so that you can get understand. So here, see the x interval we have is 0 to 1, and t is also 0 to 1. And the initial condition we are given is when time is 0, ux0 is equal to sine pi x. So this is the initial condition, and we are going to implement our MATLAB code. Very quite simple, just to follow the instructions. First, we need to choose the values, parametric values, how we can implement. And all the steps are very quite simple. So CLC, clear and close. CLC is used to clear the command window, clear is used to remove the variables, and close is used if any figure window is open. Okay, so initially you will put this statement so that all previous inputs can be removed. L is the length of the road. Okay, we are given x lies between 0 to 1. So L is the length of the road. T is equal to 1, the total time. Total time we have is 1. Okay. Alpha 0.01 we are choosing here, which is thermal diffusivity constant. You can manipulate later on. NX, what are NX? NX is equal to 50. These are the number of special grid point. Okay. These are the special grid point, and as you know, we are given in this direction, this is 0 and this is 1. We divide in this way. Okay, and according to the given condition, when we have time equal to 0, we can easily compute all these points from the initial condition. Okay, so all these points will be computed for 0 to 1. So NX, the number of the special point, grid point for the special we have is 50. Then NT is equal to 100 step size for the time. These are the time step. Okay, we choose in this direction. These are 100. You can choose 50 or you can manipulate according to your desired values, depend upon your choice. Okay, dx. If you are choosing this numerical value, then what will be dx? Dx is equal to L upon nx. This is the dx. Dx is equal to h step size for the each subinterval. Okay. Similarly, we have the step dt is the time step size, which will be t upon nt. Okay. Now, corresponding to these parametric values, we can generate line space. X line space we have is 0 to L, and these are the nx plus 1, the number of the steps for this domain. And t will be equal to the line space, 0 t is the interval, and these are the total number of points. And these are the total number of points. Okay. So nx is the step size, then number of steps will be nx plus 1. Now we want to implement the initial condition. Okay, u0 is equal to, we have is sine pi x. Okay, now all these things which we are given are here. Now initialize the solution matrix. U will be equal to zeros, nx plus 1, nt plus 1. Okay, the number of size in this direction and the number of steps in this direction. So this will be the size of this matrix. Okay, and boundary values and the initial points we are given, and corresponding to this we need to compute. Okay, so here this is the initial condition. Okay, as I show in the PPT, u:1 u0. So the meaning of this one is when t is equal to 0, all the values of x, we have u0. Okay, u0 is only used for when time is 0. So all the values will pass through this function. Okay, x is equal to 0, 1, 0.1, 0.2, 0.3, up to when we have the largest value is x equal to 1. So all the values will be computed by using this index. Okay, after that, we need to use here finite difference, which is very quite simple. Come back to presentation first. See this equation very carefully. ui n plus 1. Okay, ui n plus 1, this is the left hand side. This is ui n and alpha delta t upon delta x square u n I plus 1 minus 2 u I n plus u n I minus 1. Okay. Now you can easily compare this equation with MATLAB code. U, the value which was ui n plus 1, in the MATLAB we are writing in this way ui n plus 1. Just you need to convert in the MATLAB syntax. This is the left hand side. Then this is the right hand side. uin alpha product dt upon dx square. You can see in the MATLAB, in the PPT, this part. Alpha delta t upon delta x square. Okay. See in the MATLAB, here is alpha dx square. Okay. Then compare this part. Dr. P. Deepa, please mute your mic. Okay. So sorry, I have to mute all the mics. Here, u I plus 1 n minus 2 u I n plus u I minus 1 n. Okay. And here you can compare in the MATLAB at this place. Okay. So this is the main differential equation. Now, how we can implement, because there are two index. One is for time and one for x. Okay. So here you can see when we have this is the when n is for x. Okay, for x, see the loop I is equal to 2 to nx, because the initial value the value is 8. We need to compute only the internal values. Okay, so just 1 minute. Okay, so here this is the first value. The first value when we have x equal to 0. Sorry, when we have t equal to 0. Okay, so the first level we have the values. Now for the next level we have is I is equal to 2. So 2 to nx, we need to compute all these values. Okay, so and for the t, nt, we have to start from n equal to 1 to nt. Okay, so from 0, this value must be passed through on the right hand side. That's why we need to pass this value on the right hand side when we have t is equal to 1 and t is equal to 0, and that will be corresponding to this index. Okay, so this value will be updated automatically, and we have to apply the loop for both the parameters for x and t. So this is the loop for nx x, and this is the loop for t. And when you will execute this finite difference at the place, all the values will be computed, and now we need to all the values will be stored at this place. Okay, now we need to plot, but for the plotting, the one important thing, the dimensions of x and t must be equal. Okay, that's why we are using mesh grid. We are using here mesh grid. By using the mesh grid, the size of both the matrices will be equal. Okay, so that's why, and mesh grid for x and t. Then surface function is used here. This is the x input, then t. Okay, u depend upon x and t. U is the function of x and t. So x is here and t is here at the place, and u at the place. So u will depend upon x and t. Also, we are using here u transpose because the values of u are in the form of when you will use the transpose, then the values of x and t will match with u. Okay. So x label is there, y label is there, then we have the z label, and title is temperature distribution over time. We are using here two more statements, which are box on and grid on. Okay. So here, when you will execute this sequence of statement, our entire code is complete. And when you will execute, you will have the solution. You will have the solution. So this is the solution for this problem. And when you will left click on this figure, you can rotate this image at 360 degree. Okay, you can rotate this graph on 360 degree. Okay, so you can see here on the left side in the plane, we have x. Okay, and on the other side we have is t, and on the vertical line we have is temperature. So this is the required solution of this one-dimensional heat equation. Okay, and also you can use the animated. I am trying to use if these are correct. Yes. So if you want to animate, then you can use this statement and try again. So this is the animated graph. Okay, here you have two graphs. So when we have time is 0.18, we have this, and when we have time is equal to 1, we have this one. So you can create the animated graph also by using this statement. Okay, so this is all about the partial differential equation, how we can use finite difference method, and similar type of the problems you can use the finite difference method to solve the various type of the models by using this method. So this is all about the finite difference method. Okay. Any question related to this one? Please feel free to ask me. For partial differential equation, I choose only one example. And by using the same, you can do different type of the experiments. Okay. So we have is time left only 7 minutes. If you have any question, please feel free to ask from me. Okay, you are muted. Just 1 minute. Yes, now you can unmute your mic.
Thank you, Prof, for the wonderful presentation.
Thank you.
I have the following. I have the following two questions, sir. Can you hear me?
Yes, I can listen
Hello?
to you. Yes.
Okay. I say, what is the best way of discretizing in a linear function or derivative? Supposing in the example you gave us, maybe we have a w x all square within the problem. What's the best way to discretize that function with the higher index or the higher power 2?
When we are employing the numerical approach or the approximation method, so every method have some specific conditions, and according to that we have to choose the method. And sometimes for the different methods, we have to change the method for the exact solution. Okay, so there are so many methods in the numerical methods, and according to the problem, according to the convergence, okay, whether the solution, the method which we are applying for the some specific method, whether it is convergent or not. Okay, so the convergence is also play very important role, and also we need to compare the numerical approach with the analytical solution. Okay, so the difference, absolute error must be as minimum as our desired solution, and according to that, we have to choose. So this is in the very small period, we are not able to present everything. There are many things behind it to apply different type of the method for the different problems. For the ODE problems, there are some solvers which are inbuilt method in the MATLAB. Okay, we can use them also, just like ODE 45, you can check from the MATLAB. Here is ODE 45.
Okay. Okay. Second question, sir.
Yes. So
Hello.
according to the problem, we have to choose the method. So here you can see this is the ODE and solve non-stiff differential equations. So the non-stiff for the non-stiff differential equations, we are not able to use Euler method. Euler method will fail for this problem. Okay. So according to our problems, we have to choose the method. And if you want to check this syntax for this ODE, you can check from the MATLAB itself. Okay, these are inbuilt solvers in the MATLAB, which we can use directly. And here is the example for the same. Yes, we have y dash is equal to t, and t span we have is 0 to 5, y0 is equal to 0, and this is the ODE solver. And just we need to call the function at the place, and we need not require to write the whole code because solver itself is inside the MATLAB. So here, what is this is the function handle at the rate t, and y dash is equal to 2t. This is 2t. Then we need to put the t span. T span is 0 to 5. Okay, and this is the initial condition. And initial condition we have is y0 is equal to 0. Okay, so this is the input. Then we have the initial condition. Then we will use the MATLAB solver. This is the syntax for the MATLAB solver. And this is the command to plot the graph. And you will have this graph in the MATLAB. Okay, so there are so many MATLAB solvers for the different type of the problems, and finite approximation methods are very useful, but depend upon, again, I am repeating the same, depend upon the problem, we have to compare the results with the analytical solution, which method is more appropriate for your existing problem. Okay, then you can use the other method if the difference between analytical solution and the approximate solution is minimum. According to that, we have to choose. Okay, so as much we have the minimum absolute error, we have more accurate solution. So this is the main way, and convergence is also very important. Any more questions,
Okay,
please?
Yes, sir. I have another question, sir. Hello.
Okay. Yes, I can
Hello?
listen.
Hello.
Yes.
Hello.
Yeah.
Okay. Supposing the example you gave us find a difference. Supposing it's a velocity equation that you want to use find a difference. You want to use this find a different method to solve. You want to find the volume flow rate, which is going to be the integral of u from 0 to 1 of the d of x. How can I use find a difference scheme to integrate to get the integral of u?
You want to
supposing sir, the question you gave us is a velocity equation, supposing that I want to use it to integrate, to find the volume flow rates, which I'm looking for the integral of u from 0 to maybe boundary bottom problems. Maybe I want to now use find different scheme. Then I want to integrate from 0 to 1 to find the volume flow rates. How can I implement that in the find different scheme? Do you get me right, sir?
Your statement is very long and not easy to catch everything.
What I say, sir?
I think
Can
your
you hear me,
problem.
sir?
Listen. I think you are asking about the differential integral problem, right?
Yes, sir.
Yeah. So for that, we have to apply the other methods. So the method which we discuss here are not applicable for differential integral equations. We have the several methods because for the different types of problems, we have different numerical methods. So every method is not applicable for every problem. So according to problem, we have to check whether this approach is applicable or not. And the easiest way for the differential integral operator, we can use some integral transforms, just like Laplace, Fourier, and smooth transform is also there. Okay, so all type of the some of the integral transform can help us to solve this type of problems by using MATLAB. Okay, but there are some numerical approaches also there. For this type of the problem, sorry, I did not check any method for today's session. So this time I don't have any method in my mind. But if you need any method for this problem, you can write your problem to me. And yesterday also I told you that you can send me your problem on my WhatsApp number. And I hope that all of the participants have my WhatsApp number. Okay, all the messages which you are getting are by me and our team.
Okay.
So whenever you will send your problem to our team, automatically we will receive and we will try to provide the appropriate solution for your problem. Okay, but right now, sorry for your problem because you have long statement.
Okay, sir. Okay. Thank you.
Okay, thank you.
Thank you.
Any more question, please? I think there is no more question. And our time is about to over. And sorry, the second part for optimization technique. Someone is asking about can we use this numerical method physics, particularly in writing computer? Yes, these methods are not only for mathematical problem. You can use this method for different type of problems which are associated with physics, quantum mechanics, and engineering problems, medical science problems are there. Just like there are some mathematical models. Okay, in the all type of the mathematical model, we can use this numerical approach. Okay, so just like you can see during the COVID-19, there are several methods, and one of the model is SIR model. And to solve the SIR model, we can use this finite difference method, we can use Euler method, we can use modified Euler method. So there are many numerical methods which we can use for different type of problems. Okay, but in the beginning, it will take some time to understand how we can write, how we can examine, how we can testing. Okay, first thing is the fundamentals about the numerical method must be very clear. And for that, you need to read about the methods. Okay, the application part is the secondary part. First part is to understand the method and which type of the problems we can solve. Okay, so you can apply these methods for all branches of sciences where you have the mathematical model, whether it is a physics, chemistry, engineering problem, and biological models. Every model can be solved by using, which can be expressed in the dynamic equation, and you can apply this type of the numerical approach. Any more question, please? I can check a chat box if there is any question. Okay, there was only one question, and is Euler method inbuilt? No, Euler method is not inbuilt, and maybe in the future this can be inbuilt. But we have the MATLAB code, and you can easily. I write the code. Okay, you can use this code for different type of the problem. Okay, but also keep in mind which type of the problems you can solve by use Euler method. And there is one more modified Euler method is also there. Okay. So this will take some time to understand about these methods and to use for different type of problems. Any more question, please? So Dr. Saket is there. Okay, I think my colleague is not there. So this is all about the today's session, and the second part for the optimization technique we are not able to cover, but the basic information about the optimization technique we will share with you. And very soon we have the special program for the optimization technique we are going to organize very soon. Okay, so this will be a 1 week or 2 week program for optimization technique. We will cover all this method in the upcoming event, but still I will provide for this event content as are there. I will share with you, and I will record one method for optimization technique, and you will find in the lecture series. Okay, I will share with you after recording, but now I am not able to present here. So thank you very much to listen me very carefully. And tomorrow is the last day of the session. And if you have any question or the problem regarding the content which we are providing, you are getting everything. I think there is no problem. We upload the content in the platform, as well as we are providing you by using the Google Drive link, and which has been shared to all the participants. And I hopefully you are getting all this content, and today's content will also be uploaded after this session. Okay, and you must do some practice on this content. Just attending the session and listen the lecture, not sufficient until you not work on it. When you will work on it, you will try to some problems by using this approach, then you will have more understanding about these methods. Okay, so tomorrow we will join at the same time. Feedback link and the quiz link will be provided you after this session. I will share in the WhatsApp group, and all the participants are in the WhatsApp group. Okay, so tomorrow we will join at the same time, and certificate of participation we will inform you by tomorrow. So thank you very much to be part of this event once again. And now it is time to close the meeting. Thank you very much. Tomorrow see you again at the same time.
Thank you, Mehar sir,
Thank you,
for
Prof.
such a nice, informative talk. It will be very helpful for researchers and professors who are looking to explore the MATLAB in their study. Thank you, sir.
Thank you very much, sir.